On chain. Dear students, good evening. Welcome to GTQ session, electrical machines. We'll start with transformers. First question. I'll be showing you the question. First make a note of it. First keep trying. Give your approach and I'll be solving the solution. Kindly let me know, is it visible or not? Is the font size okay? For a specified input voltage and frequency, if the equivalent radius of the core of a transformer is reduced by half, the factor by which the number of turns in the primary should change to maintain the same no load current is. This is the question. I'll give you a hint. In this question, it was given radius is halved. If radius is halved, definitely area becomes bi-fourth. If area becomes bi-fourth, reluctance of the core becomes into 4, increases by 4 times. And here it is given input voltage, frequency are maintained same. V by F ratio maintained same. So definitely the magnetizing current also remains the same. Here don't get confused. E1, E2 means not primary, secondary. E1 is the first case, E2 is the second case. Means after making the radius of the core half, then area became by 4, reluctance became into 4. That's the case in this particular case. So as it is mentioned in the question that V and F are maintained same, I am equating voltages. E1 is equal to E2 because V by F ratio is maintained constant. IM1 is equal to IM2. This is the first equation we can make out from the given conditions of the question. Next, go back to the basic equation. Flux is equal to MMF by reluctance, like I is equal to V by R concept. In case of flux, we can write BMA MMF N into I, here N into IM, magnetizing current, by reluctance. In the first case, BM1 A1, N1 IM1 R1. In the second case, 2. And by substituting, you will get one more equation. By solving those two equations, finally you will get what is asked in the question. So finally answer is C. So many of you wrote answer, someone wrote answer is B, and many of you wrote answer is D. Ashutosh, Saujanya, Avi Kumar, Ahan Basu. I don't know how you got D as the answer. Kindly correct. Answer is C. Yes, Lakshman, IM1 is equal to IM2. Yes. In the question itself, it was very clearly given for the same no load current. Check once. I'll move to the next question. A single phase 22 kVA 2200 volt by 220 volt 50 Hz distribution transformer is to be connected as an auto transformer. Its maximum kVA rating. Maximum kVA rating. If you see any auto transformer question for maximum kVA rating, remember HV as common portion. Additive polarity. Whether it is step up or whether it is step down, it doesn't matter. HV as common winding, both input output sides, and it must be additive polarity. Single phase 2200 by 220 volt transformers, right? So HV is 2200. So make 2200 as common portion 220 as a single winding, non-common winding, additive polarity. That will be the maximum kVA rating of an auto transformer reconnected as a 2-winding transformer. So always start with single winding, simple to answer. You know, here the current rating is 22 kVA by 220. So the current rating of this winding is, capacity is 100 ampere. I2 means if you connect a load here across these two terminals, the current you can handle is easily 100 ampere. So I2 is 100, V2 is 2420. So what is V2 I2 or V1 I1? Anything you know that? It is the kVA rating of the transformer. So V2 I2 is 242 kVA. This is the maximum possible kVA rating. If you're asked a question in this, like what is inductively transferred power? Directly you can answer 22 kVA is inductively transferred power. Why? Because through mutual induction, inductively transferred power is that when it was a 2-winding transformer, the total kVA transferred through mutual induction or inductively transferred power is 22 kVA. Then what is this 242 kVA means? Extra, another additional power which is directly conducted from input to output side, because some part of the winding is common to input as well as output. So the remaining 242 minus 22 kVA, if you take, you will get a number that can be treated as conductively transferred power. So no need to put any formula, no need to calculate K, 1 minus K times all these things. Directly you can answer. Next, a 200 by 400 volt 50 Hz 2-winding transformer is rated at 20 kVA. Its windings are reconnected as 200 by 600 volt auto transformer. A resistive load of 12 ohms is connected to high voltage side of the auto transformer. The value of equivalent load resistance in ohms as seen from LV side is. This is the question. There is a 12 ohm resistance across HV side of the autotransformer, and what you are asked is the equivalent resistance seen from LV side. You can use K, you know K in autotransformer, you can use LV by HV concept, and into K square you can do, that's one thing. Or simply in the transformers, when you're transferring from HV side to LV side or LV to HV side, generally there are two currents, and if you're bringing a resistance from LV side to HV side or HV to LV, the presence of this resistance on one particular side, the impact should be exactly same on both sides with their respective currents. For example, here the current is 50, resistance is 12. So the power dissipated over there on HV side, I square R, if you calculate 50 square into 12 should be equal to, if you calculate the current here, this side, what is the current? Means, you know already V2 I2 is equal to V1 I1. So I1 is someone is asking what is this current rating here, 50 ampere. How this 50 ampere came means this is 400 volt winding. In the question, (400 volt, 20 kVA transformer). So 20 kVA by 400 volt if you put, you will get the current rating of this particular winding. That is this current rating. And this is V2, this is I2, this is V1, this is I1. If you want I1, you can calculate V2 I2 is equal to V1 I1 concept. From that I got I1. So I1 square, if this is the low voltage side, if this is the high voltage side, the impact of resistance should be same on both sides. Like that I have equated. That's one way simply you can calculate, or you can use K or into K square. Next question. A 50 Hz 220 by 400 volt 50 kVA single phase transformer operates on 220 volt 40 Hz supply with secondary winding. Then two 20 50 Hz. This is the basic transformer rating, 220 volt on primary side, 50 kVA, 50 Hz. Now it is operating on 220 40 Hz. First check, is V by F ratio constant or not? First 220 by 50, next 220 by 40. V by F ratio is not equal, then you know eddy current loss is proportional to hysteresis loss is proportional to as Bmax is not constant, in place of Bmax you can put V by F. So finally you will end up with these two expressions. Eddy current loss is proportional to V square, independent of frequency. Suddenly you will get a confusion that how eddy current loss is independent of frequency. It is not independent of frequency. It is proportional to square of the frequency. But in this particular case only, it is becoming independent of frequency. Understand that? So it is proportional to V square. In this particular case, voltage is not changed. Supply voltage is 220 only. So eddy current loss remains unchanged. But as frequency reduced from 50 to 40, as F is in the denominator, hysteresis loss will definitely increase. So answer is PE same, unchanged, pH increased. Next question. The core loss of a single phase 230 by 115 volt 50 Hz transformer is measured from 230 volt side by feeding the primary from a variable voltage variable frequency source while keeping the secondary open circuited. The core loss is measured to be 1051 watts for 230 volt 50 Hz input. The core loss is again measured to be 500 watt for 138 volt 30 Hz input. The hysteresis and eddy current losses of the transformer for 230 volt 50 Hz input are 1050. So remember, in iron loss conceptual questions, if you are given like this, combinedly iron loss, in the first case, iron loss in the second case, you have to use a constant A, B or K1, K2, anything. In the previous question, it was not like that. Individually asked, hysteresis loss, eddy current loss. If you're individually dealing, easy. No need to take any constant again, no need to do any time waste. But if you're commonly given like this, on a whole iron losses in the first case, on a whole iron loss in the second case, then if you want to segregate or if you want to separate eddy current, hysteresis, individual if you want to calculate, then constant will help you. So in the first case, 1050 is the total loss given. Eddy current loss, hysteresis loss can be written like this, because B is constant. V by F ratio remains constant. In such questions, directly you can put like this. In this case, 230 by 50, 138 by 30, V by F ratio is constant. So therefore, directly you can keep like this, and this is the first case. Iron loss with 50 Hertz. AF plus BF square. Second case, AF plus BF square. This is the iron loss. So by solving these two equations, we can calculate A and B values. Once you know A and B, you can get back to the question what you are asked. Next question. A 1 kVA 230 by 100 volt single phase transformer is operating under saturation. You know, when the core is saturated, when you apply a sinusoidal supply across a transformer primary, first the transformer will draw a sinusoidal current naturally. This current, which is sinusoidal, doesn't make sinusoidal flux in the core because the core is saturated, due to which flux establishment in the core will be flat topped. Then this flat topped flux contains a dominating third harmonic component in it. Third harmonic flux component, additional component, produce additional voltage, that is third harmonic induced EMF in primary, secondary. Then third harmonic voltage will produce third harmonic current to circulate in the primary and in the secondary. If the secondary is on no load, no current in the secondary, but primary current will be circulated. Then third harmonic current circulation in the primary will manipulate the sinusoidal current drawn by the primary first. First the current drawn is sinusoidal. Now third harmonic current will be superimposed on sinusoidal current and make the current peaky in nature. This is what you will see in excitation phenomena topic in transformers, just before three-phase transformer topic. What I want to convey is you have to bring back that particular line. Current drawn from the supply, first sinusoidal naturally, but immediately when the flux is flat topped, because sinusoidal current can't produce a sinusoidal flux because of saturation, you know this logic according to excitation phenomena topic, then third harmonic voltage, third harmonic current is produced. This third harmonic current will definitely make current which is non-sinusoidal. So the current drawn from the supply become peaky because of the third harmonic current. Then automatically there is an agreement which you see in excitation phenomena. If current is peaky, flux becomes sinusoidal. If current contain harmonic, flux becomes free from harmonic. That's the logic. So in this question you have to answer current drawn from the source is non-sinusoidal, flux is sinusoidal finally in a single phase transformer. So I want to extend this, like if you are asked a question another way, you know induced EMFs are sinusoidal, that's okay, because the current is peaky, flux becomes sinusoidal, induced EMFs become sinusoidal. But if there exists a question like this, with load or on no load, where the induced EMFs are more sinusoidal, you have to answer with load, not on no load actually. Why with load means, when secondary is loaded, there will be a current in the secondary also. When there exists any third harmonic component in the secondary, its component will be there in the primary by K. Therefore, more peaky the current drawn from the supply, means the primary current will be more peaky and the flux will be more sinusoidal and the induced EMFs are more sinusoidal than no load condition. That could be another thing in this. Next question. Star delta transformer shown above is excited on the star side with balanced 4-wire 3-phase sinusoidal voltage supply of rated magnitude. The transformer is under no load condition. The primary is star, neutral there is a switch S1, secondary is in delta, there is a switch again. If switch is open, delta is open. If delta is closed, third harmonic currents can circulate. If neutral switch is closed, third harmonic currents can circulate. That's the logic actually. So, with both S1, S2 open, the core flux waveform will be, because the switches are open, because the third harmonic currents can't circulate first, because first the voltages won't be sinusoidal. First I am talking, when voltages are not sinusoidal, third harmonic component voltage existence will produce third harmonic current. If the windings support to circulate, automatically this current will make the current drawn non-sinusoidal. If current become non-sinusoidal, automatically flux becomes sinusoidal. That's the agreement in the excitation phenomena concept. So what I want to convey is, when switches are open, third harmonic current can't circulate. So with both S1, S2 open, the core flux will not be sinusoidal for sure. A sinusoidal at fundamental frequency, flat out with third harmonic, peaky with third harmonic. None. What you will answer? Simple. Never a flux can be peaky. Impossible. Because of saturation, flux is always flat topped. So because S1, S2 are kept open, flux in the core established is flat topped with a dominating third harmonic. Next, with S2 closed, switch, S2 is closed. When S2 is closed, automatically this is a delta. So any third harmonic induced EMFs first make a third harmonic current circulation perfectly. There won't be fifth, there won't be seventh, because fundamental, fifth and seventh, they all contribute, like 1 at an angle 0 plus 1 at an angle minus 120 plus 1 at an angle minus 240, they add towards 0. But cophasal, these third harmonics are totally cophasal, 1 at an angle 0 plus 1 at an angle 0 plus 1 at an angle 0, like that, cophasal in nature. Therefore, they all add up and they produce third harmonic current. So, with S2 is closed, S1 open. When S1 is open, automatically in the fluxes there will be third harmonic components. The third harmonic component in the flux produces third harmonic voltage. That third harmonic voltage produces third harmonic current to circulate there for sure, right? So, with S2 and S1 open, S2 closed, S1 open, current waveform in delta winding is it contains third harmonic, only third harmonic, yes. I'm sorry, I'm repeating. There was a doubt why there is no fundamental current, or why there is no other fifth or seventh, only why third we are focusing. In the previous case, only third harmonic, why? There is a reason. If you take three-phase nature, fundamental, fifth or seventh, they all have a basic three-phase nature. What is three-phase nature? 120-degree time displacement. Means if you put in a calculator 1 at an angle 0 plus 1 at an angle minus 120 plus 1 at an angle minus 240, it will be 0. Or for fifth, if you put 1 at an angle 0 plus 1 at an angle minus 240 plus 1 at an angle minus 120, then also 0 only. So fundamental, fifth and seventh, they all who have a three-phase nature, the net value will be added towards 0 in the delta. But third harmonic is not like that. Third harmonic voltages are cophasal. They don't have a basic three-phase nature. They don't have any time displacement. 1 at an angle 0 plus 1 at an angle 0 plus 1 at an angle 0, like that. It will be 3. In that way, the total voltage will be add up in the closed delta and they circulate the current. That's why in the previous question, answer is only third harmonic current will be there in that delta. So whenever you see a 3-winding transformer question, remember only one thing. What we do for secondary, we have to repeat for third winding. That's it. A tertiary winding means third. The meaning, dictionary meaning of tertiary is third. Tertiary or third winding is nothing but additional secondary winding. What is secondary doing? The impact of secondary is exactly same as tertiary. For example, if there is I2 in the secondary, in the primary I2 by K. What is K? Primary by secondary turns. In a similar way, if there is I3 in the tertiary, in the primary its component will be there, that is I3 by K. What is K means? Primary by tertiary turns. Simple. For example, in this question it is given N1, N2. N1, N2. 100 turns, 50 turns. So K12. Hundred by 50, that is equal to 2. Similarly, K13, 100 by 50, that is equal to 2. So I2 is given as 2 at an angle 30. So I2 dash means the component in the primary, secondary component in the primary will be I2 dash is I2 by K. I2 by K. What is K? 2. So 1 at an angle 30. Similarly, I3 is given 2 at an angle 150. So its component in the primary I3 by K, that is K13 is 2 again. So I3 dash is again 1 at an angle 150. So I1 is I2 dash plus I3 dash. It was given magnetizing current is neglected. If it is there, no load current I0 also have to add vectorially. So I2 dash plus I3 dash, that is 1 at an angle 30 plus 1 at an angle 150. I2 dash is I2 by K12. I3 dash is I3 by K13. That's why 2 by 2, 2 by 2, it became 1, 1. If there is I2 in the secondary, I2 by K in the primary, I3 in the tertiary, I3 by its K in the primary. Transformer action. A 3 kilowatt 400 volt by 200 volt delta by star 50 hertz 3 phase 6 pole induction motor is found to draw a line current of 25 amperes at a power factor 0.4 lagging. When a blocked rotor test is conducted at rated voltage, find the stator rotor winding resistance in ohms per phase if the torque developed by the motor under the above conditions is 25 Newton meter. What you are asked is to find R1, to find R2. Here K is given. You know already K must be specified in per phase only. You know this already when we discuss transformers. Same logic will be extended here also. Because it is delta star, stator is in delta, rotor is in star. In that way the question is mentioned to you. According to the context of question, what you can do is, because it is delta, line and phase both are same. So 400 by star 200 by root 3. Then you will get 3.464. This is K according to the question given to you. We have to use this K now to find out the rotor current using K and to shift the parameters also by using K. Next you will understand that. So if you read this question, if you see this question, it is given, it is establishing a torque 25 Newton meters when it is blocked. That is very clearly given. So we'll go back to the torque formula which has R2 in it. This is current in the rotor under running condition, R2 by S. S is some slip under running condition. This question is concerned about blocked state, means S is equal to 1 I2 is basically I2, means I2 dash is running, I2 is on the starting, like that. So T is equal to 3 into 60 you have to keep per phase values. K is basically, you have to write in per phase only, turns per phase or induced voltage per phase, because it is delta, line is equal to phase. Because it is star, you have to put by root 3. So according to the context of the question, as it is mentioned, 25 Newton meter is the torque developed under blocked condition. By substituting the current, you will get this. Next, from the blocked conditions we can write something like this. There is a standard when you write turns ratio K, always maintain N1 by N2, primary by secondary. It is not a rule, it is a standard. So, when you take current secondary in the primary by K, if anyone take N2 by N1 as K, no problem, you can proceed, but then current in the primary will be into K. Like that you have to change, you have to mind that. Anything you follow, at the end of the day maintain the correct thing, like whether you go from that side to this side or this side to that side, maintain it. You have to check one thing, if you are bringing current from LV to HV side, on high voltage side current value should be low, maintain that. Whether you put by K or whether you put into K, check it. If you are bringing the current from HV to LV side, current value must raise, because on LV side current will be higher, maintain that. Whether you take K is equal to N1 by N2 or K is equal to N2 by N1, maintain this, you will get the same answer or right answer. In the same way, impedances also, when you bring from LV to HV side, whether you make into K square or by K square, check whether the values are increasing or decreasing. If you come from LV to HV side, values of R and X should enhance, check it. If you put into K square, suddenly if you get lesser value, because you are on HV side, you got lesser value than that, maintain it, means correct it immediately, check. So someone asked that why we have to K N1 by N2 only, why not N2 by N1? Anyway you can take, it's up to you, but cross check the standard. Like when you are going from LV to HV side, voltages must increase, currents must decrease, impedances must increase, accordingly maintain it. Next, second question, a 230 volt 20 HP, 60 Hertz, 6 pole, 3-phase induction motor, driving a constant torque load at rated frequency, rated voltage and rated HP, has a speed of 1175 RPM and an efficiency of 92.1%. Find the new operating speed if a system disturbance causes 10% drop in V, 6% drop in frequency. Assume friction and windage and stray losses remain constant. As you know, this is the basic torque equation, which is an approximate one, ignoring the stator parameters. This you can use for solving these kind of questions basically. In this, again what we can do is, because an induction motor is running at a low slip in general, Sx2 square is very low value. That's why we can ignore this term. Remember, if the question belongs to running conditions only, you can do that. Starting, you can't do that because S is equal to 1, which is dominating. So, under running condition, you can ignore that. Then, 362 pi numbers. In NS, 120 F by P. 120 is a number, P is a number. F is a variable thing, because see the question, 6% drop in frequency given. So F is a variable thing. So NS means F means NS, proportional to each other, you know that. So this expression can be written as T proportional to S V square by R2 into F. Generally, induction motor questions, many, which pertains to these things. If a question contains changes in V, changes in V and F, or changes in R, what will be the change in slip for a given torque, for given torque conditions? For all those questions, this formula is the best used formula. This, according to this question, no need to check R2 because you know resistance is not changing in this question, but V is changing, F is changing, right? And torque is also constant given in the question. So substitute in place of V2, what is mentioned? 10% drop. 10% drop in voltage, 6% drop in frequency. So V2 is 0.9 V1, 6% drop. F2 is 0.94 F1, substitute, and from that you will get a new slip S2. What is S1? 6 pole, 60 Hertz. Substitute S1, then you will get S2 value. Check once, you will get S2 value 0.024, and then you can find out mu F1 is 60 Hertz. V2 became 0.9 V1, F2 became 0.94 F1, substitute. S1 you know already, Ns minus N by Ns. you will get S2 because T2 is equal to T1, constant torque. So you will get S2. Once you get S2, you will get N2 because N is Ns into 1 minus S. Ns2 also will change because frequency changed. So automatically 120 F by P, new synchronous speed. This is the new speed, approximately 1100 RPM. Yes, Ns2 will change. You have to remember this because there is a change in frequency, there is a change in synchronous speed for sure. So if there is a change in synchronous speed, accordingly N also will change. So remember that for new frequency, what is Ns? Otherwise, you will end up with a wrong answer. Hope you understood. Next question. A 440 volt, 50 hertz, 6 pole, 960 RPM, star connected 3-phase induction machine has the following per phase parameters referred to stator. R1, R2, means R2 dash is given already, referred to stator. X1, X2 dash referred to stator given 1 ohm. This is the data given to you. Note down this. R1, R2 dash, X1, X2 dash 0.3, 1. 50 hertz, 6 pole, 960 RPM motor. I'm moving on to the next slide. The magnetizing reactance is very high and it is neglected. Machine is connected to 440 volt 50 hertz supply at a certain mechanical load. It is found that the magnitude of the stator current is equal to rated current of the machine, but the machine is running at a speed higher than its rated speed. Previously it is running at one particular speed at one particular slip with some current. Now same current is flowing in the motor at higher speed also, it seems. That's the logic in the question. What was that speed they are asking? machine is running at a speed higher than its rated speed, but the stator current is same. Find the speed at which the machine is running. Obviously you have to see here, previously it is running at a speed lesser than synchronous speed with some current. The current is same for a new slip, for a new speed. Let us deal like this with equivalent circuit. Easily you can get the answer. You know that the load resistance here R2 RL is R2 dash into 1 by S minus 1. So R2 dash plus R2 dash by S minus R2 dash finally becomes R2 dash by S. So this combination is R2 dash by S plus R1. R2 dash by S plus R1. 1 plus 1 square. Current is I. So first we calculated I for a given slip or for a rated slip. First case, what is I means? This is the current drawn. According to the question, what is mentioned is current is same at another case also, but for that the speed is higher. At a regular case 960, it is more than that it seems. So what we can do now is we can put a slip S. We don't know what is that slip, we don't know what is that speed. So let it be S only. Means here R2 dash by S let us put, and current must be same. So let us calculate for the same current, for the same voltage, what is that S. From S we can get speed again. If you see in this question, it is mentioned clearly, the speed is higher than its rated speed. Speed is higher than its rated speed means for the same current, the next higher speed will come in the generating mode only. So if the speed is more than the rated speed, means synchronous speed is 1000, operating speed is 960. So if it goes to 970, 980, 990, 1000 and more than that, slip automatically becomes negative. That's what it is. So we have to choose the negative slip because it is given higher speed. So it comes under generating mode then. So by applying theta concept, impedance angle concept, you can find out the impedance angle of the main winding, impedance angle of the auxiliary winding, which means the current flowing in the main winding lags voltage by 89.4 degree. The current flowing in the auxiliary winding lags the supply voltage by 89.9 degree. Almost they are very much closer to each other. And go back to the basic. Starting torque of a single phase induction motor can be expressed as TST proportional to Im Is sin lambda, or this is starting current in the starting winding, this is current in the main winding, lambda or alpha, anything, it is the angle between these two currents. So if you find what is lambda here, it will be around 0.5 degree. 0.5 degree is really very small value. For example, this is the figure given in the question. This is main winding axis, magnetic axis. This is auxiliary winding magnetic axis. Who is leading, who is lagging? Let us check. The current in the main winding lags voltage by 89.4 only. The current in the auxiliary lags more. So who is leading? The current in the main winding leads the current in the auxiliary winding. Can we say that? So Im leads Is. The flux always move from leading phase to lagging phase. So this is leading, this is lagging. First this, next that. So the motor is rotating anti-clockwise. Generally we think like that, because there is a small difference between these two currents. So we check who is lagging, who is leading, and accordingly we will answer. So because the main winding is leading the auxiliary, definitely we say the motor will rotate anti-clockwise now, according to this figure, because main to auxiliary. But remember, in this question you have to answer motor won't rotate. There is a reason. The reason is, if you see this Im Is sin lambda, lambda value is difference of 89.942 minus 89.427, which is a pretty low value, and if you put sign of that value, it is 0.000 something. You can check that 0.000 something multiplied with IMIS is almost 0. So during starting, even on no load, some inertia will be there on the rotor. So based on that inertia, starting torque should be somewhat higher. If the angle between the two currents is almost 0, like 0.5, don't help it out. That's why you should not see that small difference, and you should not answer that the motor will rotate anti-clockwise now according to the figure given. It is right. Theoretically you can say main winding current is leading the auxiliary winding current, so the flux always move from leading to lagging phase. This you can apply in the next level questions. For example, tomorrow you find this kind of question where you have a big angle, not like 0.5, not like 0.6, something like that. If you have a bigger angle, at least 10 degree, 20 degree, 30 degree, if you solve questions like that, Definitely you can answer the motor is going to rotate anti-clockwise, main winding to auxiliary. This is the way you can say the answer. But in this question you must answer 0. Motor won't rotate because the difference between the two currents angle is very, very low. So till now there is some technical issue, so I couldn't see any of your chat or comments there. So now it is resolved, now it is coming, now you can type your doubts. No, question 4 is not skipped actually. Question 4 is solved. Question 4, this is the hint. Equivalent circuit, no, this one. From the equivalent circuit of blocked condition, don't say all this. Only it was given in the question very clearly, neglecting losses, neglect magnetizing current. So there is no R1, there is no R2 dash, only X will be remaining, blocked. S is equal to 1, short circuit. So I is equal to V by X, means IBR proportional to V by F. So based on this, you can write an expression like this. Simply, you can use this expression to solve question number 4. First IBR1 is 50, V1 is given, F1 is given. Next, V2, F2 are given. So what is IBR2? Using this relation, you can solve the answer. 45 amperes we will get. This is question number 4. And question number 5, just now I explained you. All you have to do is one thing. Apply network theory basic. Find out the impedance angle of auxiliary winding, impedance angle of main winding. Then you know, based on impedance angle, the currents in the main winding and auxiliary winding will be lagging the voltage. This is it. In the question, IM lags voltage by 89.42 degree. IS, current in the starting winding or auxiliary winding, lags the voltage by 89.94 degree. So theoretically, generally one will think like this. IM is leading IS because it has lesser lagging angle, it has more lagging angle with respect to V. So comparatively, relatively, Im is lagging Is. So the flux always move from a leading phase to lagging phase. So this figure will be given in the question. This is the main winding magnetic axis. This is the auxiliary winding magnetic axis. This will be indication given to you in the question. You can check previous year GATE questions. So from main to auxiliary, this is the way the flux is passing, RMF. So the motor is rotating anti-clockwise will be the answer. But kindly don't answer that. The reason is you have to think one step ahead. What is that means? Between these two there is lambda or alpha. That plays a big role. You know already starting methodologies. We want to create some angle between Im and Is, at least some 30 or 20 degree like that, so that it can make it. If you can make 90, that would be the best possible value. Or there is another formula, you know, that for maximum starting torque theta is equal to some formula will be there in the theory, we will see. That's all. Finally what we want is more angle between Im and Is, not like 0.5 degree. 0.5 degree don't help it out. Why? Because sine 0.5 if you put, sine 0.5 degree if you put very low value. So in this formula if you put that, it's a very low value. That low starting torque cannot make the motor to start because of inertia itself. So you have to answer, it doesn't rotate. Now read sixth question. A 400 volt 50 Hz 4 pole 1400 rpm star connected squirrel cage induction motor has the following parameters referred to stator. R1 1 ohm, XS is equal to XR dash is equal to 1.5 ohms. Neglect stator resistance, neglect R1 given, neglect core and rotational losses given of the motor. The motor is controlled from a 3-phase voltage source with V by F control. Stator line to line voltage and frequency to obtain maximum torque at starting will be. We have to apply maximum power transfer theorem, because you know for maximum torque is torque is 3 into 60 by 2 pi ns I square R2 by S. What is I square R2 by S? It is air gap power. So torque is proportional to, if you put 3, that is per phase air gap power. Torque is proportional to air gap power. If air gap power is maximum, torque is maximum. So neglecting R1 given in the question, neglecting shunt branch. X1, R2 dash, X2 dash and this. You know R2 dash by S minus R2 dash plus R2 dash finally becomes R2 dash by S. So, in order to obtain maximum torque generally across this means I square R2 dash by S, that power should be maximum. Torque to be maximum. Air gap power is I square R dash by S, you know that. So, applying maximum power transfer theorem, what we can write is R2 dash by S if you notice R is given 1 ohm, means R2 dash is given 1 ohm, X1 and X2 dash is given 1.5 ohms. So in this question, it is all about maximum starting torque. So if you substitute S is equal to 1, you will get R2 dash is equal to x1 plus x2 dash. You know x is 2 pi FL. Here F is the one what we wanted. So Fm I am putting because that is the frequency for maximum starting torque. So x1 2 pi Fm L1, x2 dash 2 pi Fm L2 dash. Already x1 x2 dash values are given to you 1.5 ohms. So from that you can calculate L1 L2 dash values. That if you substitute, you will get finally Fm value. If frequency is 16.7 hertz, you know V by F ratio must be maintained constant in order to maintain Bmax constant, otherwise saturation issues will come. So if frequency is reduced to 16.7 hertz, automatically voltage must be reduced to 133.4 volts. Then only V by F ratio will be maintained constant. So this solution is based on maximum power transfer theorem. We have to equate this R2 dash with x1 plus x2 dash. By applying maximum power transfer theorem, we got this solution finally. So dear students, as it is past 8:30, I will stop here. I will take one more session on 29th. On 29th of this month only, there is a session Revise with me for GATE and ESE 2023 electrical machines. There I will be taking all synchronous DC machines, induction and transformers. That is like a big session, I think 6 to almost 10 it will be there. So in that session I will be covering all the topics, all the 4 topics. So hope this will help you in your GATE preparation. Wish you all the very best. Continue preparing as questions as possible. So I will see you again on 29th evening. Thank you.